Machine learning is such a fascinating topic to learn and to implement as well, right? The main algorithms and all the methodologies of learning are what makes this domain really fun to work with, and of course, at the same time, adds power to it. Now, regression is a common talk whenever the discussion is about machine learning or its algorithms. And with this, there are two types which are extensively used: linear regression and logistic regression. But did you know that the working methodology of these two algorithms are fundamentally different compared to each other? Well, keeping this in mind, we here at Great Learning have come up with this video discussing the differences that lie in between linear regression and logistic regression. Before we get started, I want to introduce you to Great Learning Academy. This is a free initiative by Great Learning where you can have access to over 200 plus courses with 1000 plus hours of free content on all of the trending high demand domains, absolutely free. Register now to complete the course and get your free certificate of completion as well. Check out the link in the description box of the video below for more details. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleagues, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments. So guys, what is regression to begin with, right? Regression is a very important concept in the entire world of machine learning because, both these linear regression and logistic regression, whenever we talk about these things, these two have such a profound impact on the applications we derive out of using the domain itself. So what is regression? Well, coming to regression, regression is one of these mathematical or statistical concepts where we actually use it to model a target variable based on some other variable, what we call as the independent variable that we have. Now, you can be confused a little bit about this statement, but again, we're going to simplify things down to a very simple level here, right? So think of regression like a statistical tool. Now, this tool will be used to actually plot relationship between two variables, or in many cases, it so happens that it can be more than two variables as well. But to simplify it down, we're going to take two variables. Now, what are these two variables? One variable is an independent variable and another variable is called as a dependent variable. Now look at the names, independent and dependent, right? Of course, an independent variable can do anything on its own and it will not have an impact on whatever is the output we're looking. But a dependent variable, right? So it depends on something else. It is depending on another variable or another outcome or another approach or something like that. Well, that literally is the meaning of what we're going to do with regression. We're trying to map a relationship between an independent variable to see what happens when the independent variable changes and note it down another variable, right? So when the independent variable itself changes, it so happens that of course the dependent variable who's which is running a function on it or anything like that will also change. That's the whole point of regression. If you're wondering about where regression is used, it is popularly used wherever we have to find and determine cause and effect relationships. Now, to give you a very good example of cause and effect relationships, think about the rise in the prices of petrol, right? Petroleum, diesel, or whatever it is. Now, if you just think that, hey, rise in the cost of petrol will only, affect me who's riding a scooty, who's, commuting to office and all of that, not really. It's going to affect, everything right from you yourself, right? It's going to increase the fares of travel. There's a good chance e-commerce companies will increase its prices on delivery because even they use petrol-based vehicles or diesel-based vehicles to deliver things to you. So the cost, rise in the price of petroleum can lead to a lot of effects which can be unseen at the start, and to eventually map a result, determine a relationship that exists, saying, hey, the rise of petrol leads and causes to all of these, and we have data to prove it, right? So to draw these determinations, we actually require regression. Now, to add on more points to why regression itself, right? Cause and effect relationships are one thing, but there are many other things that regression is good as well. The first thing that you have to know about why regression is required is that sometimes we do have variables, sometimes we do get data in a way where it is continuous in nature, right? Continuous variables can be like age, salary, and all of these, right? These increase on a linear level. You don't go from age 5 to age 50 in 3 days. You go 5, 6, 7, 8, and then 50, right? These are continuous variables. And then you have categorical data. Now categorical data can so be that it's the price of the house, or it is something like when someone asks you what is your blood group, you say you are O positive or whatever that is, right? That is also a type of data which is seen. Now it so happens in many cases that we have to determine a relationship between a continuous variable and a categorical variable on the other side. So in this case, the independent variable can either be continuous or categorical in nature, but the dependent variable will always be continuous in nature. This is a case in regression which is very important, and this kind of an intertwined support is what makes regression the need of the hour today. We try to find a best fit line to showcase our relationship and say, hey, here is the line which determines between 2 points, one being continuous in nature, the other one being either continuous or categorical, and this is the relationship, right? To determine it and prove it with data, facts, and to plot a best fit line, we require a regression out there. Now, it's not only the case that you always have to keep mapping relationship between, just single variables. On your screen, what you see is y is equal to f of x, right? Now, y is equal to f of x is a very popular relationship when it comes to regression. Here, as I've already mentioned, the change in one variable will affect the other variable. So at the end of the day, whatever we're talking about, the changes that happen to the variable x that you see on your screen right now will determine the changes that will happen to y, right? Because as and when x changes, there is a function that is being applied on x. Now, whenever a function is being applied on x, the output will be very different, and that difference will get mapped to y. Are you getting the differences between now to showcase of how we are trying to map this relationship? This is the mapping, this kind of a requirement in today's world, cause and effect, whatever it is, right? The fundamental breakdown of its existence, if you consider a single variable, is this: y is equal to f of x. Right. Now, to actually dive into the heart of the topic, we need to understand what linear regression is and, of course, what logistic regression is before we go on to compare some very important points, right? As and when we discuss this, try to see if you can find out the differences on your own. When we go on to take an introduction to linear regression, which we're going to do right now, and of course, when we're going to do the same thing with respect to logistic regression as well, you will find the fundamental differences in working, and I highly suggest you note it down before we actually get to the differences section, right? Then you can actually compare and see how things work. Perfect. Now, to talk about what linear regression is, right? Now, linear regression, we know what regression is. Linear regression talks about how we can plot a linearly varying, relationship, and how we can showcase this in a mathematical manner, right? Now, see, on your screen, you have a graph that denotes sales, which happens in crores of rupees, versus marketing budget, which happens in lakhs. So, if you're spending in lakhs for your marketing, what is the sales you're making in crores, right? That is what the line indicates, and each point can be mapped into the x-axis and of course into the y-axis to see the marketing campaign for that product, that service, and all of these things, right? Now, if you take a look at the linear relationship that exists between marketing budget and sales, there is a linear relationship which shows here that, hey, with a slight increase in marketing budget, our sales is actually going ahead in crores. We are investing in lakhs, but our sales are touching in crores, right? Now, it is linearly increasing. It is not in a case where you're spending more money and your returns are becoming less, right? Look at the graph. That's not the case. So you see this line here that we have drawn, right? This is basically the linear regression line. This is the regression line called as the best fit line, which showcases, hey, based on all of these individual data points, if you have to plot one line to showcase a linear relationship that exists between sales and marketing budget, this is what we would do, right? In fact, to its simplicity, this is what linear regression is all about, to map a linear relationship that already exists. Now, to go on to plot a straight line, to plot a linear line between two variables, an equation is very, very popular. It's called y is equal to mx plus c. And I'm sure you might have studied this, either in your school, in your college, or for any competitive examinations if you've taken those up.
For the people who do not know this line, this equation basically y is equal to mx plus c is the equation that governs a linear line. That this is the equation. If you put in values for mx, c, and y, you get a straight line which will showcase on a two-dimensional x and y axis, saying, hey, on these two axes, this is the line, and to govern this line, there will be an equation, and this is used to find that out. M is called as the slope, which talks about the angle. Basically, we don't directly interpret it as an angle, but a literal slope in the line, right? And of course, c is called as the intercept. C is a point where either on the x or the y axis, depending on the equation, y is equal to mx plus c or x is equal to my plus c. Based on all of these things, it will talk about on which axis is the intercept that we are trying to do. So if you plot that point down to either the x or the y axis, it will meet at a certain point on the axis. That point will be called as the intercept, guys. So it's a very simple concept when you're taking a look at it. But one thing you have to try to understand is this is the working of the line. Now, how do we make linear regression? How do we make use of linear regression to go on to use for the working of this line, right? So in the case of machine learning, whenever we use linear regression, what we try to do is we try to predict the best values for the intercept and the best values for the slope. Once we predict and get to the best values of the slope, that is when we can say, hey, there is a linear relationship, a good relationship that exists in between the independent variable y and of course the independent variable x, right? So our prediction, as close as it can get to being good, that is what makes deals the efficiency of learning in terms of linear regression as well. But y is equal to mx plus c talks about this one line. What if we have multiple variables that we have to deal with, right? Look at the equation on your screen right now. We're talking about y is equal to m1x1 plus m1x2 m3x3 all the way to mnxn plus c. Right now, this is not one line that you see, but it is a plane. We're talking about multi-dimensional planar plotting with this particular line. It is y is equal to mx plus c, but if the m were supposed to be called m1, m2, m3, if you had multiple span of variables, this would become a plane of multi-dimensions, right? It is a pretty fascinating concept to see that we can plot relationships based on this. We can find the intercepts. We can go on to predict what slope value is required for us to have accurate relationship built as well. And these kind of statistical concepts and mathematical concepts are what makes machine learning fun, right? So, using all of these concepts in the case of linear regression, when we go on to evaluate models, how do we evaluate models in machine learning, right? We find error rate. We try to see the difference between what was predicted versus what exists. If this difference is very high, we say that, hey, the error rate is very much high and your machine learning algorithm can, produce incorrect outputs. If the error rate is low, of course, it's accurate. And our goal at the end of the day is to make sure the error rate is kept low, right? That's the thing. In the case of model evaluation here with linear regression, we make use of multiple ways of how we can determine the error and to bring it down as well. You have the MAE, which talks about the mean absolute error. You have the MSE, which talks about mean squared error, and of course RMSE, which is root mean squared error, which is again a very, very popular form of evaluating a model based on its performance, right? So these will give you the error rate, and the goal is to make sure you bring the error rate as much as possible down. Right. That was a linear regression. Now to talk about logistic regression, right? See, logistic regression is another fascinating concept which is working on the basis of probability. In linear regression, you usually you ask questions, you try to plot a linear relationship saying, what will be my salary when I touch age 35? Or what will be the salary when I have 10 years worth of experience, 15 years worth of experience, something like that, right? You can map your age and your salary increases like that. But with logistic regression, you talk about the chance of it happening. If I ask a question saying, hey, at age 35, can I get XYZ salary? The answer to that will be a yes or a no, right? You don't have the probability of saying maybe or maybe not. we're going to get to that as well. There are chances of that occurring too. But if you have a binary outcome, in a binary outcome, we discuss a probability of a yes or a no, one or a zero, true or a false, right? I'm sure you guys already know this. So here, the entirety of logistic regression works on this principle as well. We call it as maximum likelihood estimation. So we try to see what is the most likely outcome. Is it one? Is it zero? And we eventually give out a prediction saying, hey, probably it is leaning towards one, so it might be one, or probably the outcome is showing somewhere near zero, so the model thinks that the outcome is zero as well. So this is a very important thing which you should know about logistic regression, and right now I'm sure you could have plotted a simple difference that exists between linear and logistic, right? Perfect. In the case of probability as well, one important concept which I have to remind you all is that whenever there is an occurrence of an event and the occurrence of that event not happening as well, right? So the probability of me getting an XYZ salary and the probability of me not getting an XYZ salary, if you put both of these together, it has to be one, right? Your probability cannot be anything less than zero, or it cannot be anything more than one. It is a hard bound limit between 0 and 1. It's basically a percentage. If I say probability 0.8, we're trying to say, hey, there's an 80% probability that it might happen, right? Something like that. Now, in the case of logistic regression, to go on to plot a relationship and say, hey, you know what, with the maximum likelihood consistency or the situation, to get to this, we cannot just have zeros and ones. So we have to increase the range of our search, increase the range of pattern hunting, and of course, increase the range of throughput as well. In this case, we take this hard limit which stays at 0 to 1 and expand it to minus infinity to plus infinity. So we plot a curve which looks like an S. If you write the alphabet S in capital, we plot a curve which looks like that, and eventually using that, there's many other concepts which will govern the working of it. Now, since we're talking about 0 to 1, you have to know something called as predictive power, which is an important concept here. Now, see, with predictive power, let's say if your value, the value that you obtain is somewhere around 0.02 or less than that, it means there is a 2% chance of something occurring. So it means that your prediction is almost, it is not helpful. It is almost like saying, hey, it will not occur, right? But if your information value is between 0.02 and 0.1, it says, okay, so there is a weak percentage, 10% probability that something might occur. And if it's between 10 and 30%, we say, okay, it's a medium predictor. It is predicting really well. And if the accuracy of prediction lies in between 30 to 50%, we say, yes, it's a strong prediction. There's a good chance we can rely on this. And of course, if it's greater than 0.5 or greater than 50% in terms of predictive power, we say either it's an amazing predictor which can predict really, really well in terms of the binary outcomes, or that something is wrong and it's doing something incorrectly, right? It's either one of these situations. But hey, whenever the information value is somewhere around 0.4 or 0.5, that is usually the starting sweet spot, as we call it. It is mostly good enough in terms of making predictions as well. Now, there is another concept in logistic regression which you must know about, which is called as ROC, or it's called as receiver operating characteristics curve. No one usually calls it the full, the name. It's usually abbreviated in a very common sense. It's called ROC, and it is vital that you know what ROC is, right? That's the entire point here. So with this curve, we put out a graphical representation to show that, hey, if we have a binary classification model, how do you determine the performance of this, right? So this curve is used to determine saying, hey, this is what is the actual thing. We can predict strongly saying that something, a picture is either a cat or a dog, right? If you have pictures of cats and dogs and you want your machine learning model to determine that using logistic regression, you cannot just show a cat and say it's 100% cat unless it is trained on it, right? That time, well, it might think that, hey, a cat has a tail as well, even a dog has a tail, so it can get confused there. It can predict it incorrectly too. Now that is, all of these things, the determination of accuracy is also shown in the ROC curve as well. So we have some metrics of accuracy here. These metrics of accuracy depend on four things. We have true positives, false positives, true negatives, and false negatives. So using these, we set a threshold value saying, hey, if you are crossing either of these values, it means that either the model is going towards accurately predicting our binary outcome, or it's deviating far away from it, right? An ROC curve would look something as you see on your screen right now. For 100% relationship, we have the middle line that determines it. And if you keep going up and up and up, as you can see, there's a curve between, there's a curve A, B, and C. So here we're trying to say, hey, with this particular curve, we can show that you can use the metrics of accuracy, of sensitivity, specificity, F1 score, and all of these things to say, hey, this was the percentage of accuracy of detection of this event happening, right? You can see the probability. We start at 0 and we go to 100%, or it's usually 1, 0 to 1, right? So in this 0 to 1 relationship, usually on the y-axis we talk about how many true positives were found, and of course on the x-axis we always plot how many false positives were found. So if you keep moving away towards the side of true positives, it means your model is getting more and more efficient. It can predict things correctly, right? A false positive is a wrong situation or an incorrect prediction which can hurt the accuracy of the model, and of course the accuracy of the result itself, right? This is ROC curve. And all of these things that I just mentioned, right? Precision, recall, F1 score, and all of these things, these have their own formulas. Precision, recall, F1 score, they are very important formulas. And these formulas, the values that you put into these formulas are based on this particular table. It's also called as the confusion matrix, where we try to understand situations where your model has predicted things correctly versus it predicting things incorrectly, right? So you have true positive, true negative, false positive, and false negative. As you can see on the column header, we have predicted yes and predicted no. So if your prediction says yes, and if your actual model is also yes, it means correct. Your model predicted right. But if your actual says yes and your model says, hey, no, it's incorrect, well, it's a false positive, right? Because in the real world it is yes, but your model says no, it says 0 instead of 1. That is a false positive. Similarly, if your actual case is no, but your prediction says yes, it's a cat, while it was actually a dog, well, it's a false negative. Again, if it's the actual case which is no and you're predicted as no, well, that is actually a good thing, right? It's not a cat. Your model says, hey, no, this is not a cat. Perfect, it works, right? So what we hunt after whenever we take a look at accuracy is the values of true positive and true negative. False positive and false negative hurt the accuracy of the model, and we try to keep it as minimum as possible. And with an effective, efficient model, that happens to be the case as well. Right. Now you know what linear regression is and what logistic regression is. So let us quickly compare some of these points of some of these points which are very important for you to know. The first thing is the dependent variable type. As we already seen, in the case of linear regression, we try to use these independent variables to predict what happens to the dependent variable, right? But did you know that the dependent variable has to be continuous in nature for us to use linear regression? Well, in the case of logistic regression, this is a little different, because here you can also use a categorical variable to be the dependent variable, and in that particular case, the type of regression that you do, the outcome, the problem that you're trying to solve becomes fundamentally different, because one, we are talking about a continuous variable, which is the dependent variable. In the other case, in logistic regression, we're trying to say, hey, your output is categorical, your dependent variable is categorical in nature, right? So in this particular case, the working itself becomes fundamentally different. The second point in our comparison is going to be the application, right? As we've already discussed, linear regression is extremely popular whenever we have to build and determine a linear relationship in terms of cause and effect problems, right? There it's very, 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 very common. And the common term for cause and effect relationship problems is called as regression itself. In the case of logistic regression, however, since you saw the working 0 and 1 binary outcome, we use it for classification purpose. Dogcat classifiers, or loan default prediction. Will this person default a loan if the bank gives him or her a loan, right? The answer is an either yes or a no. Can the person repay the loan back? You don't say I can pay half of the amount, 3/4 of the amount. You have to give a yes or no answer, right? So there we're talking about logistic regression as well. The third important point in discussion is the working of it. I already showed you the best fit line, the linear line that we want to use. And of course, we saw the ROC curve as well in the case of logistic regression, right? So this linear line in the case of linear regression, which is also called as the best fit line, versus how we use this S-looking curve, or of course, not a straight curve in the case of logistic regression, which helps us to classify it. Either says, hey, it is either 1 or it is 0, right? In this particular case, again, you can see the fundamental difference that exists. The next point that we have to talk about is definitely the output. In the case of linear regression, what usually happens is the output is continuous in nature, right? We've already discussed this. A continuous variable can be something like predicting your age, predicting your income, or something on these lines. In the case of logistic regression, it is binary, yes or no, 1 or 0. So this is a very, very important concept that you have to have as a fundamental knowledge when you're comparing between linear and logistic regression. Right. Coming to the next important point, we have to talk about the threshold value. Now, see, whenever you're trying to perform regression, whenever you're trying to find a best fit line, you really cannot set a threshold. You cannot say this is the minimum. I want to do, I want to find a relationship from here to there, which you can definitely do, but there is no hard and fast limit which says without this threshold, linear regression will not work, right? So that makes the threshold value not a compulsion in the case of linear regression. But then, hey, in the case of logistic regression, you have to put a threshold value compulsorily to say, hey, if it crosses this value, it is either 1, or if it is below this, it is a 0. So without this, your machine learning model will not be able to classify, because it cannot function. It cannot know at 60% of probability of detection of a cat, should it call it a cat or a dog? At 70%, should it be a cat? At 80%, at 90%, even at 99.3%, if you set a threshold, it can still call a cat as a dog, because your threshold value was something around that, right? So with this, it is very common that you have to understand how the data itself gets distributed, right? Well, again, here's another very interesting, fascinating difference point. In the case of data distribution, whenever we talk about linear regression, we make use of the Gaussian distribution, or of course the normal distribution, the bell-shaped curve, right? In the case of logistic regression, however, since it is binary in nature, we use, guess what? Binomial distribution, right? Of course, this is something which you could have guessed, and I hope you've been mapping these differences yourself from the start of the session until now. Right. Now, to quickly show you guys the functioning of both linear regression and logistic regression in the case of using Python, I'm using Google Colab. Google Colab is basically a Jupyter notebook hosted on the Google Cloud platform. Let us take a look at 2 quick practical implementations, right? Let me clear all the previous outputs. Perfect. Let's wait for the runtime to connect. And the runtime is initializing and connected. Perfect. Let me zoom in a little more so you guys can see. Right. The first thing that we're going to check out is linear regression, guys. In the case of linear regression or logistic regression, the first step is to always import the data set, import the libraries and all of that, right? So we'll be importing NumPy and Pandas. NumPy is used for numerical computations, and Pandas is used for data storage. Basically, it provides series and data frame structures for us to store data. And we have sklearn or scikit-learn, as it's called, as a very popular library which is used for machine learning. Now, let me quickly go on to import the data set that we are talking about. Perfect. And that's imported, right? Now, as soon as I hit play, basically what we're trying to do is we're importing the data set and we're printing the first 10 rows of the data. In the case of linear regression, we're going to be considering this very fascinating problem called as the Boston housing dataset, where we are trying to predict the price of the house based on all the other factors, right? We're trying to map a linear relationship saying, hey, if your house is very old, usually there's a chance that the price will drop, right? There are so many things that you can consider for the change in the price of the house. If you have to predict the price of a house, you'll be taking a look at a lot of different things. How far away is it from the industry, how much tax you have to pay, what's the age of the house, how many floors, what's the parking area. So you can take a look at 100 different parameters and eventually put out a relationship saying, you can find the best fit line, right? So again, you can see CRIM stands for crime rate. Basically, even crime rate affects the price of a house. If there's a lot of crime going on in front of your place, your property value is definitely going to decrease because the neighborhood will not feel safe to stay in, right? So we've just printed out 10 such columns to showcase that, hey, this is the data set, and we're going to be predicting based on this, what happens to the house price as well. The first step that we have to do is, of course, to clean the data. In this particular case, our data set is already clean, so there is no need to remove any NaN values. NaN stands for not a number, right? So whenever I ask you the tax on the house, what is the tax that you have to pay for the house, you don't say that the tax is not there or something, right? It's not a categorical answer that you give me, it's a numerical answer. This numerical answer, right? For example, when I ask you what is the tax of the house, you don't say the tax of the house is O positive. Doesn't make sense. Perfect, right? So sometimes it happens, your data is incorrect, and you do get to a point where it gives you nonsensical answers like this. To avoid all of this, we require pre-processing. In this case, it's already done. Perfect. The next thing that we're going to check out is to actually split the model, the data that we have, into training and testing data set. The training data set is what the machine learning algorithm is going to use, in this case for linear regression, and the testing is what we later show to the model to verify, to see if it has learned. Just like a concept of where you learn from your textbook, go write an examination, and you're evaluated based on it, right? So in this case, we've put in 70% of the data for training. Well, how do I set this number? Well, look at the test size. If the test size attribute of the test train split function says it is 0.3, it means to say that 30% of the data is going for testing. If 30% is going for testing, how much remains for training? 70, right? Pretty simple. So I'm going to hit a run, and our data is now split. The next stage, now if you're a person who was stumbling upon linear regression or logistic regression for the first time, if you're wondering if you have to write 100 lines of code for the machine learning algorithm to learn, well, it is literally 2 or 3 lines. Here we are trying to use a linear regression model, right? So first, to load the model, LR equal to linear regression is the function that we're going to use, because we have to import linear regression from our scikit-learn library for this purpose. The next thing is we are going to give it the training values so that it can train, it can understand what is going on with the data. Later, to predict, to see if the model has actually learned anything, right? Model evaluation, we go on to give what data to it? Testing data, right? X underscore test, as you can see. So we provide the testing data later after the model has learned, to see if it has understood something or not. And now the model has learned, and we have seen if it has learned anything or not. But to predict it in a metric, to predict the error at which it has either learned or not, is this. Well, it is showing that the error for linear regression on this Boston housing data set is at 5.54. Now you would need a value to compare this. If you use the same data set by working on another algorithm, maybe the KNN algorithm, or maybe a random forest problem, when you take the other applications, you can compare the efficiency of the algorithm itself. You can say, hey, on this data set, KNN works amazingly well. On the other data set, maybe linear regression is very powerful, right? To do all of this, we go on to check these algorithms. So linear regression is perfect. Next, let's take a look at logistic regression. Even in the case of logistic regression, the step 1 is very much similar. We have to go on to load NumPy. We're going to be loading pandas, and here we're going to be doing a little bit of data visualization. So we also load matplotlib. Matplotlib is a wonderful data visualization library in Python. And of course, the next step is to import the data set. But to import the data set, first I have to bring the data set itself to Google Colab, which I'll do. And that should be done. Perfect. Now in this particular case, as soon as I hit run, it's going to import the dataset into the current working environment, and as soon as I hit dataset.head, it's going to print the first 5 rows of the dataset. Let me explain what we're trying to do here. In the case of logistic regression, we're trying to have a classifier, right? We're trying to classify something. So what are we doing here? We're trying to predict the age of we're trying to predict if a person purchased the product or not by using his or her age and his or her salary as well. Now it so happens that using age and salary, a person who started their career right now might not be able to afford a Rolls Royce, right? May or may not be. You never know. If the person's first salary can afford a Rolls Royce, well, good for them, right? So it's not just a Rolls Royce example. So basically, think about Amazon or any other e-commerce giants who wants to analyze what is the age of the people and what they think is the estimated salary. So who can afford all of these, right? Now, not everyone in the world can afford the most expensive phone on the market or the flagship phones, right? So again, to predict all of these things, we require the use of this. But there are other things in the data. We have user ID, we have gender, and all of these, which of course we do not require. We only require age, we require the salary, and to predict if this person bought a product or not. So let us filter it out. Let us remove user ID, let us remove gender, and let us hold only these two columns to use. And of course, the last column is what we're going to predict as well, right? That's what we did with just 2 lines of code. The next thing is pretty simple. We are going to split the data for training and testing purposes as well. In this particular case, the testing size is 0.25. What does this mean? This means that 75% of the data has gone into training and 25% of the data has gone into testing, right? Perfect. The data is split now. And the next thing, we have to use something called as a standard scaler. Now, the standard scaler is used to make sure that there are not a lot of variations whenever you're working with the data. So to bring the data into a normal form and to normalize it and to work with it, we require feature scaling, without which again, you will not know what value to set where, and of course how where is 0, where is 1, what are you trying to predict, right? To get to that point, you have to align your data towards that, and that is what feature scaling does. Perfect. The next thing that we're going to take a look at is model fitting. Model fitting is when we actually go on to use logistic regression by passing it the training data, right? Again, 2 simple lines of code and it is done. And what do you do after the machine has learned it? You see if the machine has learned things correctly or not. That is when model prediction comes into the picture, and you pass the testing variable to it, right? Once you pass the testing data into it, it is going to find the difference that exists between the testing and the training, and that is where you evaluate. That is how you say, hey, the model has learned something or not, right? You remember the graph we spoke about, the confusion matrix, true positive, true negative, false positive, false negative, and I told you that these 2 values are the ones which we are concerned about, right? Let me go back to the presentation to show you these important values. Perfect. Look at this. So what we are concerned about is the value of true positive to be high and the value of true negative to be high, because these are the accurate cases. False positive and false negatives are incorrect cases, and we want these numbers to be low, correct? Look at what our logistic regression model has done. Perfect, right? So we have these 2 values to be very high, which means that the accuracy of detection is good, and of course the incorrect cases are low as possible. Now you might ask, saying, why aren't the incorrect cases 0? Well, if it was 0, it means your model is 100% accurate, and that is a pretty difficult thing to achieve, right? Now, as I told you further, there are many other metrics of accuracy that you will be involved in: precision, recall, F1 score, and all of that. And that is exactly what you see on your screen right now. So you can find the precision, you can find how accurate is your model functioning to predict the cases to be a binary 0 or a binary 1 as well. And if you compare the entire accuracy, the entirety of the logistic regression model, and say, okay, so entirely what is my model accuracy? How well is it performing? Out of 100, it is performing by giving us an 89% accuracy, right? So that's an amazing thing. So guys, this is the differences that exist between linear and logistic regression. So what did you guys think of these differences? To learn more about these, make sure you're checking out Great Learning Academy. It's an amazing place where you can learn courses and enroll into them and learn them, and of course get a certificate of completion absolutely free of cost as well. You have a lot of courses on machine learning that are present on Great Learning Academy. And of course, make sure to subscribe to the Great Learning YouTube channel and hit that bell icon so that you don't miss out on any of these important videos that we are putting out. Right guys, with that, if you have any comments, any feedback, or any suggestions, or any more points of difference that you think are important for linear regression versus logistic regression, or your views on these differences as well, make sure to head down to the comment section and do let us know. We'll be more than happy to help you out with your queries there. On that note guys, stay safe. I'll see you on the next one.
I want to introduce you to Great Learning Academy. This is a free initiative by Great Learning where you can have access to over 200 plus courses with 1000 plus hours of free content on all of the trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion as well. Check out the link in the description box of the video below for more details. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.